Okay, so I'm here again with Neil.
Again.
He's again the head of the computer science department in Statebox. Again, professor there. And now he's going to talk about the links between category theory and functional programming language.
Okay, thank you very much. So I was going to do that, but then asked me if I could focus a little bit more on data types, and in particular the sort of data types that Ghani was talking about. So that's what I'm going to do. I'm not exactly certain what the depth of knowledge is here and what people want, so I'll sort of a mixture of some category theory and some motivations, and then some functional programming which follows on from it. So this is essentially how do you do data types categorically. So, I mean, the first thing to do is, I guess, talk a bit about motivation. So, I mean, we've seen that, there are all these different notions of type systems, different notions of data types, and Ghani talked about a few of them. Acronyms I don't really remember, like XML or JSON or something else. And it's this thing that always happens. You just get everyone coming up with a new little definitional language who says, oh, we can do this, we can do this. So we say, oh, we can do this, we can do this. And someone says, oh, we can do this, we can do this. And if you're like me, with a very small brain, your brain starts to hurt. And you're like, what's all going on here? And it seems
Calm down.
Yeah, calm down, everyone. Stop talking so much and start thinking a bit. And what you kind of want to do is you want to step back and I think have some sort of common language or some common meta language for what is going on here. What's the fundamental structures? Each of these things have different features, and some of them are good and so bad. But you want to have some kind of deeper analysis. And I think that's why, in my experience, the category theory has been very successful in providing an analysis of data types, and I'm going to tell you about that. Okay, so when you're a functional programmer, and I'm going to try and relate this to functional programming, although I might forget to at various points, so feel free to, at every point, say to me, but Neil, what's the functional programming? So we want to do programming. I think one of the ways that category theory has been very useful in computer science, or in theoretical computer science, is it has underpinned all this functional programming. Again, you don't want functional programming languages to just go off and say, oh, here's some stuff, and here's some stuff, and here's some stuff. It has to be right. And the category theory has helped us do that. So what I want to do is I'm going to talk about, first of all, the simple data type from a functional programming perspective. And then we're going to try and stand back and use this to motivate the more abstract treatment of it. So when you talk about in Haskell or in a functional language, the data type of natural numbers, what do you have? So if you're Bourbaki, you say the natural numbers are God-given. But we're constructivists, we want proofs, we want programs to build things, so we don't do that. We construct them. So you typically have things called introduction rules in type theory or in functional programming. So type theory to me and functional programming are pretty similar. They're sort of different, but they're sort of similar. For some people, functional programming is just an executable form of type theory. For others, it might be different. What do when Fred starts scowling at me? Anyway. So for here, for these types, you have an introduction rule. So you want to say, how do I build an element of a type? How do I give you, in this case, a natural number? Well, you say, well, 0 is a natural number, and you say n is a natural number. The successor of n is a natural number. Good. No one's going to disagree with that. But that's sort of not quite enough. Because once you've got a natural number, what do you do with it? You want to produce things, you also want to consume things. So these are called elimination rules. And for the natural numbers, the elimination rule is what's called iteration. So what does that mean? It means that, say you've got some type x, and you've got a particular element of x, and you've also got a map on x. So you could think of, x is your collection of Petri nets, for example. So you've got a particular Petri net and a way of transforming Petri nets into other Petri nets. Or it could be something else. It could be anything. Okay, so given this amount of data, then I can produce a function from the natural numbers into x, and I'll call it the iterator with u and v. So what does it do? So then you have computation rules. So these rules produce a natural number, and they allow you to take a natural number and consume it and produce something else. And then you have computation rules, and what do they do? It says, well, what happens if this number happened to be 0? So the iterator of u and v at 0 equals, I've got to give you an element of x, I'm just going to give you u. And what happens if I have the iterator u and v at another natural number, maybe s of n, for some other natural number n? Well, what do I get? Well, of course, I can use recursion, so I can apply the iterator u and v at n. This gives me an element of type x, by definition, and v will transform x's into x, so I can just apply v to the result. So that's a computation rule. And sometimes in type theory, these are also called beta rules, for beta reduction. This is really computation. I heard someone say once before, talking about the Petri-nets, oh, but where was the computation? So in functional programming, in type theory, this is the computation rule. It says, you know, you've got a function, you give it some structured input. If I just say the input is x and you don't know anything about x, well, you can't do anything, you can't do computation. But if the input happens to be a result of an introduction rule, so you have elimination next to introduction, then computation fires. Sometimes people write arrow to say you reduce this. And this is just simple recursion. You can see it's a recursive call function at n plus 1 equals function at n processed a bit more. Okay. So you don't need to do any category theory or any type theory, you can write this in Haskell. And this goes back to the 1930s and the study of recursive function theory. So, very good. But the question then arises, what about other stuff? You know, what about lists? And what about streams? And what about trees? And what about vectors or lists of a given length? You know, lists of length 5. What about printable stuff? So, for example, in Yellow's talk is very much interested in, I want these types, but I want to serialize them. He wants that serialization built in. So it's no longer just a set of natural numbers, it's a set plus a function which for every element will tell you what its serialization is. And also, you know, these are just sets. But maybe you want to make a structured Petri-net, you know, that says, you know, this Petri-net is got by doing something and building some other stuff on some other Petri-nets. Or you've got, what other things might we come across? Blockchains. You might want to define blockchain recursively. You know, this blockchain is, you take a previous blockchain and do something to it to produce a bigger blockchain. So what happens in the end? So the problem about this kind of type theoretic functional programming approach of introduction rules, elimination rules, and computation rules is it's not quite clear how it generalizes. It is rather syntactic, you know, and you write these horizontal lines, if I have some stuff, I produce some more stuff. But in general, for all we want to do, it's not clear how to generalize it. So we want a really powerful theory which tells us what's going on, and then we can just instantiate it over and over and over again to get the equivalent of this, but for much more sophisticated stuff. And that's what the category theory gives us. It allows us to get away from the syntax. Okay. So the key technical definition is that I'm going to talk about is initial algebra. So if you like, the subtitle of this general title is initial algebras. That's a technical concept, and I'm going to show you how they use them to make more and more complex data types. For those of you who know about it, I'm not going to talk about, in a data type theory talk, I would also talk about final algebras typically, but I'm not going to talk about them because those who know about them know that it's a simple extra little bit, and also it doesn't correspond so nicely together as wanting a finite type theory.
Are they obtained like with duality arguments?
Yeah, you just turn the algebras around and get
okay.
algebras. I'll sketch it in a moment. So the first thing I need to do is to try and move away from the syntactic presentation to something more abstract. Okay, so first of all, let's look at the introduction rules. So the first thing says I have an element 0, and just to make it make the notation uniform, I'm going to say it's a function from 1 to that. An element of a set is a function from the one element set to that set. And I've got S is of type nat to nat. Now using, we've seen coproducts. To give two such things is equivalent to giving 0, S. You can pair them up together, so it's a function from 1 plus nat to nat. So 1 plus nat, an element here is either a natural number, in which case you can apply S, or it's from here, in which case you apply 0 to get 0. And what you see here is that, in general, I'm interested in this structure. But here I've got a pattern. And in general, if I have a data type and there's more constructors like trees would have leaves and nodes and stuff, and so you'll have leaf and node or whatever your constructors are, they'll take some stuff and produce your tree. So you're going to get much more structure here. It'll always be into your data type, but there'll be something to do with your data type. So we're going to abstract this and call this is f of that, where f of x is 1 plus x. In general, to do different data types, we just change our f. If you're a type theorist, to do different data types, you write different numbers of lines and different sort of colons in different places. But the category theory is sort of bundles that up into just the choice of a functor. That's quite a beautiful, simple abstraction. If you imagine essentially you've got polynomial stuff going on here. Each of these is a plus because you've got different choices, and then you could have several inputs, but there'll be a times in there, so you get this big polynomial thing. We'll just call it a functor and not really worry too much about it. Okay, so then I'm going to define an algebra, an F algebra. So if I've got this functor, and remember that's like the signature of the data type, that represents the constructors that I want. So an algebra will just be a map from f of something to something. So it's actually it's a set x, it's an object x, and a map of this form. So you should think of, this is just model theory in a way. You've got a signature, and that's represented as a functor, and you want to talk about a model, and a model is just one of these algebras. It's a categorical way of talking about a model. You can sort of see it as a model because, for this x to be a model of your signature, it means if you build up new stuff, that's what f does, it builds up new constructors, new bits of data. Well, to be able to embed it back into x, that must mean x had the structure you need to absorb all this new construction. So it's like a model, like a group is a set with some extra structure. So I could have written a model for f, but we call it an algebra. Okay, and then we get one of the most beautiful definitions. Oh, here's a board. It's rubbish from the top, never mind. Oh, is it possible that I can get this in? Is that going to work?
Yeah, sure.
Yeah. So we start with our functor. Remember, that's a signature of our data type. The associated data type is the initial F algebra. Is the initial F algebra. So for a moment, when you see that, you think, oh, big new words, F algebra, I've only just heard that. Initial F algebra, what's that? It's sort of got an overhead for those who don't know what's going on. But what I hope to show you in a minute is that it's a very simple statement, if you know what this is, and it actually gives you all of this stuff, and even more. So all of this stuff which you thought were initial were things that you have to come up with yourself by some magical process of intuition and divination and creativity. No, you just derive it from this definition. Machine-like, you type this in, you type F into your computer, you turn the handle, and all of this comes out automatically. And I think this is the sort of thing you were wanting before, this idea of, you can spit out, various different things automatically from your definition. So I should explain how this happens, because it's really magic. You see, well, Neil, you take f of x to be 1 plus x, the most trivial, simple polynomial you can, and you say you can derive all of this from that. Really? So the answer is yes. Okay, well let's see how this works. So the initial F algebra, I'm going to write that as mu F. So mu is for initial F. Right, well what do we know? So let me just reverse engineer. I'm going to take the definition, I'm going to produce all of this stuff. What do we know about the initial F algebra? Well, first of all, it's an F algebra. It's the initial F algebra, so it's an F algebra. So of course, I have an algebra structure, but in particular, I have this algebra structure. I have this initial algebra structure, and it's often called in on my initial algebra mu f. So it's f of x to x, and x is going to be this particular object called mu f. So the fact it's an F algebra means I have a map from f of it to itself, and that's what I got here. So the constructors of your data type, or the introduction rules, are exactly this. So the constructors, or the fact you have introduction rules, they come from the fact that you have an F algebra, speaking abstractly. Okay, so I've explained how this part comes from the idea of an initial F algebra. Now let's talk about the elimination rules. Okay, so why does this look like the way it is? Why does the elimination rule look like the way it is? Well, let's box up U and V into one thing. Again, using the property of coproducts. What I had before was just a map from 1 plus x to x. And again, you see, oh, there's the functor, 1 plus x. So you can see the premise of your elimination rule is just an algebra for some other object x. So the fact that this is an initial algebra means that if I have some other algebra, let's call it alpha, and I have my initial algebra, which is the data type, then because this is initial, we've not really talked about it, it means you get a map here from the initial thing to the other thing.
So morphisms of F algebras are just a couple of arrows that make those diagrams commute.
Yes. So exactly. So if you've got one F algebra and another F algebra, you can form a category of F algebras. I've told you what the objects are. They are just these F algebras. And the morphisms is a map between these things called the carriers, such that if you apply F to it over here, the diagram commutes. So yes, so we have a category of F algebras.
So why is it called the associative?
Well, this is an English language term, it's not associativity. The data type given or defined by it or constructed by it.
I have a question. This looks very similar to morphisms between algebra and Moore algebras. Is there a relationship?
Yes, exactly. There's a very deep relationship. So for those of you who know about it, a similar term arises when you use monads. So notice I start with a functor. F of x equals 1 plus x. Accidentally, it is a monad, but we're not noticing that. that's a coincidence. It's a red herring in the English language. But yes, so when you study algebraic theories, you often have their models. And categorically, you have a monad which constructs all the terms. So there's a monad which says T of x equals the free group on x, and that's a monad. Now, they have a notion of algebra. Okay, that's a model, because you can talk about what a group is. A group is a set with a this and a that and the other. And it's a model of the theory of groups. But those algebras are slightly different. Because you have a monad, you have a unit. And so the F algebra structure has to respect the unit. And because you've got a monad, you've got a multiplication. So the F algebra structure has to represent multiplication. So basically there you've got a richer structure. In fact, you've got a monad means that you're building stuff up, but it's closed. If you do T, build some syntax, but then you do it again, T squared.
Yeah, because there are terms of terms and there are
Exactly.
terms.
But because this is a set of all terms, if you do it twice, you're not getting anything new, you can collapse it down. Whereas here, what we're doing is we're not building all the terms. This is, if you like, one layer of terms. So if you had some terms before called X,
okay,
this gives you one more layer. Essentially, if we iterate this func to F, which is what this initial algebra is doing, then we would get a monad.
so you can always produce a monad out of this.
You can always, given a functor, you can always produce the free monad on that functor,
Okay.
which consists of, so in my world, doing data type theory, the functor builds you one layer of terms. It's like a signature, it's a set of operators. It's not all the terms, it's just one layer of terms.
And then you do it.
If you iterate it like this, you get the set of all terms. If you put variables in, then you get the free monad on that functor. So there is deep connections.
Okay.
And then an F algebra for the functor is exactly the same thing as an Eilenberg-Moore algebra for the free monad on that functor. Same many, many things. But I would say for one, I'll wrap that comment up by saying that kind of thing about algebraic theories, equational presentations, Navier theories, universal algebra, it's very nice, but there you're studying equations as well, groups of equations. In data type theory, we're not doing equations, so just bear that in mind.
But then you have a sort of analogous, strange way to do a sort of Birkhoff theorem. Like in this case, you are not studying equations, but if you do that procedure, you can get the equational theory associated with this structure.
Yeah. So you're telling me that in the richer setting of not just pure syntax, but syntax plus equations, you can do things like Birkhoff theorems, and you're right, you can do that categorically, but that's a different talk.
Yeah, sure. No, but it's nice to see that.
But it's nice to see that, yeah.
Jump from one to the other depending on what you want to do.
Exactly, yeah. Okay. So, what have we got here? So this is an abstract diagram. So if you remember, given some other algebra, because this is initial, it means that there's an algebra morphism from the initial one to this other algebra. So I've called it fold of alpha. Fold is a word the functional programmers use. I'm trying to link it with functional programming terminology. But now, let's have a look at the type of this fold. So the type of this fold says, give me an algebra, and I'll produce a map from the initial algebra to the carry of the algebra. That's exactly the elimination rule. It says, give me an algebra, and I'll produce a map from the data type I'm interested in to the carry of that algebra. So, in other words, I've explained elimination rules by the map of algebras. So remember, I wanted to convince you that there's quite long and detailed syntactic analysis of what makes data type can be treated abstractly using some very simple categorical techniques. And I've done 2/3 of it. And what are these computation rules? Do they also arise? Well, remember, this diagram has to commute. So that means if I apply the iterator to something that's been constructed in, remember in is the constructors, so in this example 0 and s. So I apply fold to 0 or to s, the diagram commutes. So I get the same thing as recursively, that's why we have capital F outside the fold. So recursively apply my map to the substructures and then apply the algebra map on the outside. And that's what this says here. You can see it very well here. If I have the eliminated function, if I apply it to a constructed term, I make recursive calls on all the substructures and then apply the algebra to the outside. So in fact it's a map of algebras, gives me both the elimination rule and the computation rule.
So are you always guaranteed that an initial algebra exists for a functor?
Okay. So that's another sort of question you might ask. So certainly, if you want this stuff to exist, I've shown you it is exactly the same thing as requiring initial algebra. And I know I've told a lie there, but if you know the lie, I know that I know the lie. It's a small thing, I don't want to go into. So, do they always exist? Well, that's the same as saying, does this syntax make sense? Because you could try and interpret this in any category, and that's one of the powers of using category theory. Because if you just wanted to find sets, like the natural numbers and trees, you may not want to do all of this stuff. But actually, we wanted to find all sorts of different things. You know, if you care about recursion, you might want to work with complete partial orders. So you have to do all of this stuff, but this has to be interpreted in complete partial orders. Or if you like metric spaces, because you want to measure distance, all of this has to make sense in metric spaces and say contractive maps. If you like topology, all of this has to make space in continuous maps and topological spaces. If you want to do Petri nets, you know, what is a natural number? How do you represent the natural numbers as a Petri net? Well, this gives you the answer. You basically interpret this, but you have to interpret it in Petri nets. And of course, sometimes you can't. So the answer is, initial algebras don't always exist. I can give you a simple example if you wanted. But asking for the initial algebra to exist is no different from asking for the syntax to be modeled. This is just the syntax written in very collapsed, neat algebraic formulation. I'm not doing anything new. I'm just translating it into what I hope to explain, convince you is a better algebraic syntax.
So here was the functor, was it the free functor from sets of monoliths?
Here, you can see from the definition that the stuff you're interested in, either an algebra for the elimination rule or the shape of the constructors, shows that the functor you want is f of x is 1 plus x. And roughly speaking, after all, you get to read it off very simply. 1 because I've got one constant, x because I've got a unary operator. So for example, if I wanted to do trees, so let's say, right, let's do trees here. I won't do the whole example, but this starts to show you the power of this stuff. I could write all this stuff out for trees, you know? I might have to think about it as well, because there's a lot of stuff going on here, you know, what about all these different rules. But categorically it's simple. So I would say f of x, well let's do the data type I'm interested in. So the Haskell data type, data tree equals leaf, or it's a node which consists of two subtrees. So that's a Haskell data type. So I'm not storing data at this point. I either just say I've got a leaf, it's an atomic thing, or it's a node which has two subtrees. My experience, I can automatically write down the functor. F of x equals, remember I'm constructing one new level of terms, so I need one leaf and it's a constant. Or, the plus, I have one binary constructor. So it's binary because I've got two subtrees, so it's x squared. I have one of them, so it's just 1x squared. If I had, say I had two different types of node. Again, binary trees, but somehow some nodes are called node and some nodes are called node prime. Then I've noticed I've got one constant and I've got two binary constructors. So, and simply now, from writing this functor, which I can expect from the signature, I immediately get all of this stuff down. Just follow the pattern I wrote down here. Say the initial algebra will give me an algebra map. I'll get my introduction rules. Given any other algebra, I get a mediating map. Type that sentence and you get the elimination rule. The fact that this diagram then commutes gives me my computation rules.
I was just wondering what the domain and codomain of the functor was. Which kind of
Okay, so this is the second strength of category theory. If you go back way into the history of programming languages, you know, what are these programs? So a long time ago, a naive attitude, I should say, is to say these programs are functions. They take sets in and sets, and they produce sets. You know, the natural numbers is a set. So if I want to take that attitude, I'm working on sets. So my functor is a functor on the category sets. You know, my semantic entities, my denotational semantics are sets. But what people realize when they're studying recursion is that you know, this is like factorial of n plus 1 is, when you're studying recursion, you can't do that on the category sets. It does not have enough structure. So Dana Scott, in his famous work on domain theory, you know, he figured out that you can use, well, he started off with complete partial orders, and then he worked on omega complete partial orders, and this is the start of domain theory. So sometimes that could be on omega CPO. And like I said, these days you can do it on anything else. I mean, if you're interpreting your programs as contractive functions on metric spaces, well, then your functor is on the category of metric spaces.
The only requirement is that you have an endofunctor from a category.
Yeah.
In a category.
Yeah. So the choice of what category you're on is a choice that you make as to what do you think your programs are doing. You know, if you think they're continuous functions in topological spaces, then you know you look at your data type declaration, you write the functor, the shape of the functor, and you think of it as a functor on top. I meant to write top. Topological spaces.
So,
and then you have to do the stuff that Fabrizio asks is, well, you can write this functor and you can interpret it on any of these categories providing they have plus and they have times. This and one, and this goes back to what Yella was saying. So you need some, you know, you can't give your semantic interpretation of your language an arbitrary category. You need basic stuff like plus and times. To not have that is to try to do logic without and and or. It's a bit daft. And then you need to ensure that these initializers exist. And I won't go into it, but actually they tend to. There are very simple conditions that you can verify in the category to make sure that they do.
Do you need also 0 in this setting? Or like,
yeah, where's 0?
yeah, it's not nowhere to be found. It's like
Right, yeah. I mean, you do want 0 because I guess, you know, you're building up this type, this rich collection of types, and you definitely want 1. Okay? Yeah. And you definitely want plus. You want to take sums of types and products of types. So this is Yella's language. It has 1, it has plus, it has times, no argument. What I'm doing is taking his grammar and saying, really speaking, for what you wanted to do, your finite types, you should still have what you call cleanly star, what we would call initial algebras, or type theorists would call inductive types. It fits in your serializability desires, and you get rich things like natural numbers, or trees, or lists, so you can have all of that stuff. But of course, we could have 1 plus times and inductive types, whereas 0. We may as well have 0. You want 0, so you don't need 0. The functors don't tend to use 0, but for other reasons you want a 0 type in there.
Then basically this means that you can get the clean star for free out of this construction.
The cleanly star is this construction.
Exactly.
Yeah. I mean, this is a category theorist. So cleanly star is a language theoretic thing for finite iteration. And finite iteration on functors is what we call.
This is booming. It makes everything much simpler now.
You get all this stuff for free. Okay, so so if you want to take the first thing you could take, if you want to now switch off or something else, it's the category theorists have worked out how to do data type theory in a very abstract way, which is very powerful because it gives you all this stuff wrapped up solely in the definition of a functor. And the shape of the functor is not even complicated. It just clearly matches the structure of the signature that you write down. But the second most important point is that they've solved the problem of what about if I'm working in different, you can say categories, but if you're not a category theorist, you say, well, what about if I'm a topologist? You know, what is the natural numbers in a topological space? What is the topology on the natural numbers? As a set, the natural numbers are obvious. Is it obvious what the topology of the natural numbers is? Well, you compute it by working with interpreting your function on the right category. So this is a great strength. And we'll see in the rest of the talk, I'm going to use the strength that this theory does not need to change when you use different categories.
So, can it always be expressed as a polynomial like this?
So, there are functors which are clearly not polynomials. And we get the same discussion that we had before. This general theory is very general. It can work for all functors. But if you work with all functors, then you might have some problems. For example, some functors on the category of sets don't have initial algebras. Some functors on other categories might not. But also they're more powerful. Some functors can't lead to data types which can't be serialized. So,
Like a string.
yeah, yes. So, so what was your question again?
Oh, can they all be expressed?
Right, exactly. So they can't all be expressed. So one refinement of this theory is say, okay, now this is a powerful theory, but we want to cut down and not work with all functors, but only work with some functors that have this nice, that have serializable properties. And smaller grammar, more properties, better behaved. And if we want to do that, we'd have to enhance the theory, and we could do one of two things. One is to, what Fred mentioned, use something called containers, which are very nice. I won't talk about them. It's something that that comes with type theory, called the W type in Martin Lewis' original type theory, and then myself, Torsten, Connor, Fred, various people have tweaked the theory of W types. And they basically say, consider functors of a certain shape, and you derive better properties. And the rest of my talk could be about that, but it won't be.
And also, why are we restricting to indo functors?
Because for the F algebra, you need a morphism from fx to x.
Yeah, exactly.
And you can't do it
Oh,
if
yeah,
you're
yeah.
not the same kind.
Yeah.
Good question, Ron. Okay. Any other questions, or shall I move on?
I had one, but I
Yeah.
forgot it.
Sorry?
I had one, but I forgot it.
That's fine. So this gives you, so if you like, this gives you all sorts of nice data types as initial algebras. But sometimes you want to do more complex things. You know, nowhere have I put in here the fact that these are serializable. And nowhere did I talk about this special collection of 0, 1 plus times and that kind of, you called it something like internalizable, or in Fred's universes. So descriptive, self-descriptive. So I'm going to talk about some other ideas.
Yeah, before you go further, you basically gave in this way a model of a natural numbers object that works in any category in which this is possible.
Oh.
But we know that there are also other formalizations of like a natural number objects, for instance, like the Topos theory.
Yeah.
So my question is, do these two different ways of formalizing coincide usually, or they diverge? Like.
So I will give you this definition. My opinion, I think it's true, and maybe you have a counterexample, but there is only one definition of a natural numbers object. It is the initial algebra of 1 plus x. Now in a topos, if they say this topos has a natural numbers object, or you say, or you prove something, you are showing that fact. You're showing that that topos has that structure. So in topos theory, yes, they have natural numbers objects, but it's exactly this. You're assuming this.
Coincide.
Yeah, they are the same thing.
It's literally the same thing.
Yes. There is no other definition of natural
They
numbers.
never presented in this way in topos theory, so it seems pretty unrelated when you see
That's
it.
because if you unwind the definition of topos, an elementary topos, which has a natural numbers object, when you unwind the natural numbers object part of it, you get this. You have to have an object, let's call it nat, with a map from 1 plus nat to nat, such that for every object x with a map from 1 plus x to x.
Okay.
So this is all captured in there. Category theory is one of these, like, if you don't, some people, I believe, like everything written out because they feel comfortable. Nothing's hidden from them. They can see it all. You know, I understand that's psychology. There's nothing wrong with it. It's just the way some people are. Some people, like myself, can't handle all this stuff written out. The formulas are just too long. The brain is too small. I'm about a third of the way along. I lose track of where the brackets are. These people tend to like smaller formulas, but much more dense stuff. And category theory is like that. You put a lot of structure into your category that you're working in. Each of these terms, you've read Kelly's books. A Kelly page of A5.
Isn't that?
Yeah, in any other person's script, it's like neutron star material. It's like 5 pages of A4. So this can be frustrating. So yes, the topos theorists are doing this. They say, oh, natural numbers object. They just said all of this stuff.
Okay.
And why don't we incorporate the iteration of the functor itself, since it's an end-of one? Would that have meaning?
Yes. Let me get back to that. It'll crop up in a bit. So far these functors, I'm not describing them. These are just in the external world. If you want to have a natural numbers object in your language, then you have this functor and you want this initial algebra to exist. So I'm going to take you through a little bit more data type theory. And what we're going to do is get more and more sophisticated data types. So far, what we've got, they're just polynomials, if you like. So they're tree-like structures. Anything is a polynomial, so you'll either have some constructor which takes n inputs or n inputs. It's a tree-like structure. But there are many more sophisticated things you could do. So for instance, I think you mentioned blockchains of a given length. So here's a type, vec. Right, so vec of n, and of course lists of length n. Of length n. So that's a data type. We don't want to understand it using a new technique. We don't want another theory of data types. That's just replication. It shows you haven't understood what's going on. If we've understood what's going on, this basic theory will cover this stuff. vectors. Okay? Let's look at the definition of vectors. So, data. So this is a dependently typed structure because it's a type, but it contains a number itself. Sorry, Fred, I hope I'm not giving you a talk. Good. So in Haskell stroke AGDA, you'd write data, vec, and type nat, or something where. So you've got constructors. So you've got, 0. So that's something like type vec. 0? No, vectors of length 0 uninhabited. You have to be careful.
Fair enough.
Let's write successor. So this takes a vector of length n, gives you a vector of length n plus 1. So 0, what's the type? Is that vector 0, vec 1, vec n plus 1, n plus 1.
Why do you call 0 just like nil and then it's...
Pardon?
You're going to speak about non-empty there.
Yeah, exactly. So the thing about the type of vectors of length n should have vectors of that length. Maybe there's some kind of... there's no data here, there should be some data here. Now you see the point, whereas previously we're giving you one type, one set, or one topological space, what we have to do, but it's one thing. But now, what I'm doing is I'm giving you a type, a set, a thing, for every natural number. Right? So this is not one set, this is a collection of sets, more sophisticated. And moreover, to define vectors of length n, I need to know about vectors of length n plus 1. So I can't give you vectors of length n in isolation from vectors of some other length. There's a nice data type of lambda terms which is the same. In fact, it's so nice I'll write it down. So I think this is one of the most beautiful things I've seen since I became a computer scientist. You all study untyped lambda calculus, so you've all seen it. It's fundamental mathematical structure used in the 30s to do recursive function theory. But it's a bugger because you've got to do alpha equivalence. It's just not nice. And it doesn't fit into these nice data structures. So these are my untyped lambda terms where the free variables come from the type A. So what is it? Well, it could be a variable, it should be of type A, or it could be an application. So far nothing surprising, it's a bit like trees if you like. You've got two substructures, and to define lam A you're using lam A's, recursive substructures. Of course the difficult thing is abstraction, and you have an extra free variable. So I'll use the maybe monad from Haskell to write that. And I think that's just very beautiful. That's the untyped lambda calculus as a Haskell data type using the maybe monad to do alpha conversion, already built in. There's no need to quotient. And when I was a young lad doing my PhD, to define the untyped lambda calculus, you built some preterms up inductively, and then you cut out, you did a quotient. So here you get it for free. The only reason I mention that, it's another example where you're defining a type, and the type is indexed, but you need the type indexed at a different type. So this is more sophisticated. So these are things called inductive types, and they came along in, Peter Dibier did a lot of work on this stuff in the 90s, is that right?
Can you explain how this works with the main?
Sorry?
How does it work with the main word? What is the word?
Maybe it's just 1 plus. So you're just saying I've got a lambda term whose free variables are 1 plus a. So you have this 1, this extra free variable, that's the bound variable.
What are you finding?
Let's look at the type of abs. So the type of abs, the constructor, it says it takes one of these things and gives you a lambda term in free variables. So you have a lambda term where the free variables are either called in left of star or in right x, where x is of type A. And then you get a lambda term of type A, and that's because you're bound by that free variable.
Oh yeah, so basically 1 is the variable that you're abstracting.
Yeah. Abstracting.
1 is the x that then becomes lambda x point, whatever.
Yeah.
Okay.
Yeah. Except because it's 1, it doesn't have a name, so you can
exactly.
alpha equivalent. And then you do all this stuff about initial algebra semantics and the data type, which I'm going to show you, and you write your folds, this mediating map, and you can do substitution. It just goes smoothly. It's really brilliant. Okay. But that was just another example. So the point I want to make, let's going back to vectors, is the following. So you see here,
Why 0 is type n plus 1?
right?
Non-empty vector.
Huh?
Non-empty vector.
Yeah.
Oh, so you still need one slot, basically.
Yeah, because so how do we make a vector of length n? This definition is telling us how to make a vector of length n. That's what constructors do. They say this is how you construct an element.
So maybe you should call it fin instead of vector.
Yeah.
Make it clearer.
Okay. Yeah.
Because they aren't vectors.
Yeah, okay, because for me a vector of length 0 is not a vector. It's
Ah, right, because I haven't got any data in it. Okay. Fin. So this is
So this is a type with n elements.
It's like
And there's no type with 0 elements because that's your bottom type. Your point.
Should it be fin 0?
no. If it was fin 0, then I would be saying here's an element of the finite set of 0 elements, but the finite set of 0 elements doesn't have any elements. That's the point about it.
Maybe it's easier to just do vectors that allow that also have empty vectors. I'm not sure.
So if you do vectors, then it really is.
But is n
Makes
free
it.
not formula?
So what?
Is n free not formula? Where's the, I mean...
N is bound here. So I'm defining, this is sort of, this almost, I don't know if it's exactly out there, but it's sort of out there. You say, I'm defining a type fin. It's parameterized by a natural number n.
Yeah.
So therefore I know that fin has type nat to set. It's a type parameterized by a number. And here are the ways I can construct it. So let's look at stuff first. It's not a constant. It's a constructor. It takes a proper input and gives you an element. It gives you an element of fin n plus 1.
Is that n the same as that n?
These ends are all the same.
There's an implicit for all n.
success for I get it. It's like attaching something else
Yeah.
to this bunch of stuff.
Yeah.
But yeah, 0 equals
Yeah.
fin n plus 1.
So it's like not 2 fin and 2 fin at the successor, but you can figure out the n. But you should kind of send it in.
I mean, I don't really want to talk about this data type for the whole talk, but this line tells that 0 lives in fin 1, fin 2, fin 3, etc. Okay? This
Is
oh!
it the same 0?
line,
Is it the same 0?
No.
oh, maybe, should I call it 0? Should I call it start?
Oh, so that's like saying the empty set is in every finite set.
Yeah. Yeah.
Oh.
But I don't understand, it's the same 0 or the different 0?
It's just the first element of this finite type
Yeah.
some number of elements.
It's a different zero. It's one for every n.
Okay, but they're called the same 0.
I mean, I guess in terms,
Okay.
I guess I was right. I wrote 0 because I was thinking like this. Fin
Oh,
of n has
yeah.
n elements.
So the 0
So
taking
I-
arguments.
Yeah,
Okay.
you could think of it 0 sub 1, 0
Yeah,
sub 2.
yes.
Okay, so maybe it's 0 in brackets 1.
Yeah.
If you, yeah, I guess if I wrote for all n,
Yeah.
and here for all n, then I could put 0 and 1
Yeah.
and 2.
Yeah, okay.
So it's, oh yeah, because 0 basically represents a sort of element in fin.
Oh.
Yeah.
No, we were thinking that 0 was like a type of fin. Like,
No, this colon means
yeah, now it's
it's a
clear.
membership.
Yeah, okay, yeah, now it's clear.
Okay. I'll just remove that to keep the syntax cleaner. So the main, probably a few levels, where I want to get back to is to point out that this is a more complex data type because you're not defining one thing, you're defining a nat index collection of things. I've written sets, it could be other stuff. Okay, and moreover, fin of n depends on fin of n plus 1, so you can't define it individually. So what can we do? A, reinvent the wheel, start from scratch, because initial algebra semantics is just about defining one set. But no, we don't have to do that. We can change our category and do initial algebra semantics in this category of nat arrow set. So that's a new category. And if I say let's do initial algebra semantics in this category, then my functor should be a functor on this category. Okay? And so, what functor should I choose? Well, remember, this is building up one layer of syntax, so if K is like the terms I've already built. So remember, I'm not building one type, I'm building a family. So I've already built this family. So K of 0 will be the terms of type fin 0 I've already built, and K of 1 will be the type of terms of fin 1 I've already built. Okay, and then I need a function from that to set. So I've got one way of making something of type n plus 1. Is that right, Fred? Let's see if it's right.
Yeah.
So, I've built up some terms already, and now I want to know if I do one more layer.
You're defining point-wise, please.
Yeah, well, because I have to define this functor, so it'll take something of type nat arrow set as input. I have to give you something back of type nat arrow set. So I'll give you a natural number, and I have to give you a set. So if K is the terms we built up already, when I apply one more level of constructors, what number of constructors do I have of type n plus 1, indexed by n plus 1? Well, I'll always have 1, because 0 always lives there, and for every term of indexed by n that I've already built, I'll get another one. Okay, so, let's step back and I want to show what I'm doing. I've got a more complex data type. It's not called an inductive type, it's called an inductive family. Yes.
That's not the full definition, right?
That's the definition of the functor.
What happens at 0?
Yeah, you have to say the zero or something.
Sure.
That's where 0 comes in.
That's where 0 pops in. Here, yes. So, what was I saying? Right. So I'm defining this family inductively, and it's just initial order of semantics. All I needed to do to capture this much more sophisticated idea of data types with indexes is to move to a more sophisticated category. And then I just write down a functor, and I do its initial algebra semantics. The initial algebra will give me the constructors, the elimination rule. Sorry, if I take another algebra, then I get a map between the families. That'll give me the elimination rule, and I'll get the computation rule. So all that stuff I derived before, which you might have thought was obvious, but cleanly done, when you start getting more sophisticated data types, it's not really clear what you could write down. You derive it from just writing a choice of a category and a relatively simple functor.
But the ones and the zeros in that expression are different, because I think, like, the one on the left is the one in natural numbers, while the one in the right is the terminal object in set. Exactly. Okay. Yeah, that's.
So this is a type nat.
Yeah.
So this is all type checked by this type, and you're right, you can infer those types.
So if we said what the eliminators and elimination and computation is for this?
Yeah, I've said, by saying that, that this type, fin n, is the initial algebra of this functor f, I've told you.
Yeah, I know, implicitly.
Well, explicitly. So that's my claim, that's the nice thing, that it gives you a recipe, now you just go and compute it. It's just engineering from now on. So, I mean, sorry, to take your question seriously, if I had more time, I would do the example. I'm happy to sit down and do it with you, or anyone who wants to, and I'll just do exactly the same thing.
But how do I know this initial algebra is?
Okay, so that's the same question we had before. So, and I didn't answer it before, I want to again, there are general techniques, or maybe I should do. So, okay, I'll tell you. So there's a nice general theorem which says initial algebra exists if you've got a functor. You'll know a little bit of order theory. If you've got a monotone function of a poset, you can start at bottom, f squared at bottom, least upper bound, and if your function preserves least upper bounds, that's a fixed point. It's a categorical version of that. So if your category's got an initial object, it's a bottom element. If it's got omega co-limits, that's least upper bound. If your functor preserves omega co-limits, you'll have an initial algebra. It's the same theorem. And what's nice about all of this stuff, because it's finite-tree, that's why we might want all the functors, that preservation of omega co-limits comes for free. The other stuff is just properties of your category. Do you have initial objects? Do you have omega co-limits? Pavel will recognise as a appreciative category because you've got set there. It's all for free. It's very easy.
Oh, so this is where you need the 0. You don't need it necessarily to define the functor, but you need it to infer that you have initial F algebras.
Yeah, so you have your syntax and you have your semantics. So 0 plays a role in the semantics to start off this initial algebra chain. It can also be a type that's very useful in writing out functors like this.
So are there any other kinds of pre-sheaves that are explored in this?
Yeah, all sorts of pre-sheaves. I mean, so for example, this is a set. So it's a very simple pre-sheaf. Let's imagine we did initial algebra semantics on some proper pre-sheaf. Now what would change there? What would change is that when you write down your functor,
Yeah, but define
this is now a category. So previously as a set, I just needed to define it on the objects. Now I need to define it on the morphism. So this F, I would say if I had a morphism from n to m, what about I need something from fk of n to fk of m? And you'd be building more structure in. So people who do this sort of stuff, when they want to automatically define substitution on lambda terms and stuff like that, they use that to get renaming. So again, it's a choice. The more structure you put in your category, the more stuff you'll derive from your initial algebra semantics. If your category is very simple, you'll just get a set. The more complex it is, the more structured the object you're defining is. And I want to do 2 more to get closer to what I wanted. Okay, so this was initial algebra semantics done in pre-sheaf categories or in index sets, which gives us inductive families, very popular in the 1990s. It was going to happen, wasn't it?
This is the punchline of the talk.
Right. So I'm going to do 2 more types of data types, 2 more sorts of definitions. And I'm moving towards what Ghani wanted. So, so this is the thing about internalization or descriptions. So far, our functors and our data types have lived outside of our language. We've got syntax of an individual data type, and we're represented by a functor, and we get the data type from the initial algebra. But what about saying, what is the language of data types? In other words, can we have a data type of data types? And that's what you were doing. Or a description language for data types. So Connor in our research group has done a very large amount of work on some really impressive stuff, how you can convert, you can do modular data types, so you can take a data type of lists and you cross out the data, you get the natural numbers and sort of building all that stuff.
What is it?
Connor did some work on ornaments, which is a very
No, I did a lot of this stuff.
Anyway, can we have a data type of data types? In other words, can I have something which says like, a type, let's call it data. So it's a data type, I'll call it ty, where. So let's say, I'm going to try and do the example you had. So z for 0 is a type, O for 1 is a type, plus is a type, but actually it takes 2 types, gives you another type, and times. Okay, so yeah, it's a data type whose elements are built, or anything you can build from this kind of stuff. Okay, very good. But actually there's no semantics in here. I mean, I've called this PL, but this could have been times as well, or it could be exponential, or it could be something else. So we've not done enough stuff. Well, it could be constant, yes. So, and in your work, from what you were writing down, you noted this, and you also said, I want to have a decode, where, let's give it, I'm going to call it, I'm going to call it T. I'm going to call it TM, TM for terms. So TM should take a type and give me a set. So it'll take something in here and give me the set of elements. So in sort of data type theory, these are often called codes or names. They're the name of the type, the name of the set. And then TM maps each name to the actual set that it represents. Okay. So, for example, TM of Z, this is supposed to be the empty type, so we give it the empty set. Or the empty type. 1, oh, that's a terrible
Yeah,
name.
recalling.
Let's call it 1.
Yeah.
So TM of 1, my interpretation is this is the unit set. Unit. 1 PL, oops, sorry, TM of PL of T1, T2 should be, well, I want to know, so this is supposed to be plus. So I want the co-product of whatever the type represented by T1 is and whatever the type represented by T2 is. So I want
Yeah.
the co-product. Times TM, T1, TM, T2 times. Okay. So, very simple. But this is more sophisticated than the situation we had previously. So what I'm doing is I'm taking you on this sort of journey of data type theory. We were in the 1990s, but now we're in the early 2000s, where you see we're defining a collection of sets which are indexed, like before, but previously it was the natural numbers. It was given to us beforehand. But now we're simultaneously defining TY. So it's an index family of sets where the index is also being defined. Okay? So, let's take C to be this category. Choose a set and a function from X to set. This category is also called found set. So, first of all I had set. Whenever I say set, you can think of C. First I thought of C, then I had index objects, I arrow C, now I'm talking about found C or found set. It's a different category. It's more complex because this X changes. See, as I build up more elements of TY, then this is increasing.
So sorry, how is this category defined?
Right, so this is sloppy type theory notation. An object of found set is a choice of, firstly, a set, and secondly, a function from that set into set.
Okay.
And the difference is previously, in the previous example, there was no choice. It was always NAT, because the indexes didn't change. Now I'm changing the indexes as I build up the data.
And morphisms are a couple of arrows that make diagrams commute.
Yes, X set. If there's one family, Y to set, there's another family. And a map of families is a map on the indexes such that the diagram commutes. There are other situations where you're doing other bits of category theory where you want just a map and inclusion.
So it's a slice category over chosen.
It's set arrow, to be honest. Because the function of X to set is also a function into X, so it's just a function. Okay, so and then this leads to something called, if you think of this properly, this is induction incursion. So it's a very advanced way of forming data types where the data types are indexed, but the indexes are simultaneously being built up. And this is like pioneered by Peter Dubier and Anton Zetzer in the 2005 to 10 sort of period. And it's very advanced, and most people don't use it and they don't fully understand it. But what it allows you to do is build up exactly what you wanted. Universes, they call them universes. A universe is a set of codes, and for each code, a meaning. And what they allow you to do is instead of asking the programmer to use a grammar of types that's God-given by the JSON designer or whatever, or the Haskell compiler, you define your own collection of types, your own universe, and then you can program with your own universe. So it gives sort of, not the definition of an individual data type, but the definition of the schema of all data types to the programmer. So it's a really cool thing. I don't think it's been anywhere near as exploited as it.
Why is it called induction incursion?
Because the idea is that this set is defined inductively, but the decoder is defined recursively. So I should say, our very own Frederick in his thesis came up with the beautifully named induction, which is similar, except that these things are defined inductively. So, it's an ongoing field, there's always more things to do.
Do you have recursion?
No. You're being silly now. You betray your ignorance. Your first question made me think you were shit hot, and now you betray your ignorance.
You can only define recursive things out of inductive things.
Explaining a joke is never a good idea. Right, so I'm going to finish in a moment. So this is kind of like, you know, the sort of maximal stuff that I've done. So again, I've worked on this stuff with Fred and various people. But we haven't talked about serializability. I mean, this is kind of like the grammar you wanted. It's a universe. It's the kind of universe you wanted. I should say that, you know, one variant I might do is I might put a natural number in as an index for free variables, a type with some free variables in, because then, you know, I can write this. So nothing changes there, but then I can write mu, which is type. If I have a type in n+1 free variables, I get a type n free variables, and then the decoder for mu of something. Well, I have to write down the semantic expression. That's the cleaning star. Yeah, so I can put cleaning star in this algebra, but then I need to talk about the number of free variables. So, but the mathematics is all. It's all just initial algebra semantics. Once you know your category and you know your functor, turn the handle and you get your introduction rules, your elimination rules, your computation rules. Like we did for natural numbers, it's pretty brilliant.
Now your category is supposed not to X to set if you introduce that.
My category for doing this. Oh, so here, yes. So my when I've got this,
you have to put a nut in your definition of category.
Yeah, yeah. So with the black nut there, I have to change my thing. I think I will.
Yep.
So for every natural number.
No, it's the X. X goes from nut to set.
Yes. Okay. So certainly, so remember X, that's its indexing structure. That's my intuition. And so when you look at the indexing structure, it's nut to set. So. And then here, I guess,
for every n,
X of n to set. You know, so the category, you know, that's part of the categorical methodology. Rather, when you do complex things, you know, you can either just wrap your head over the complexity, or you shift some of the complexity into the category and keep a reduced amount of complexity to still deal with. So we've got complexity here, plus initial algebra semantics. And the claim is that's better than just writing it all out.
So wait, are you saying that you solved 9 and yellow's problem in 15 minutes?
I would not want to be so bold. I mean, I'm very much aware that as a theorist, you know, it's just this. You guys want to do some sophisticated things. I don't know anything about JSON. I know how you translate it into JSON. But I know that if you want, I know this is the core of modern data type theory in its advanced form.
Yeah, but
and what you're doing, you know, if you want to do it cleanly as a meta language, you would do this, and then you'd say, right, now how do I translate this into JSON?
Exactly. I mean, from this is a super clean explanation of what we want. So now it's just like trial and error to engineer this into something. But
now data TI is just an arbitrary choice too, right?
TY.
Yeah.
That was just because I wanted a universe which had 0, 1, plus, times, and cleanly star, because you mentioned that one. I could have other things. So, for example, this is very sophisticated. You get universes closed under dependently type structures, so the sort of stuff Fred will talk about. So, you know, you want a universe closed under, you know, which has a natural numbers, but also sigma types and pi types. I mean, complex stuff. That's all taken care of.
So, as far as you know, you haven't heard of any applications along these lines at all?
I mean, I do think that there's a, you know, this kind of data type theory, either done in type theory or in category theory, with dependent types, which Fred will talk about, is extraordinarily sophisticated. Dependent types gives you enormous power to say, you know, in your form, if you've answered yes here, go to this bit, if you've answered no, then go to that bit. Or, much more sophisticated, if you said, you know, one of these 5 answers, extraordinary power. And I doubt form theorists have any idea, really, about the sort of things that could be done with dependent types.
That's a probably a stupid question, but you say your category is, like it's from X. X was before, it was just a set. Why not it like X is dy? So your category is X is a set?
Here.
So before you index it?
Yeah, then it was X of type set.
So why is it why is it not x is ty? Because we're defining ty as well?
Yeah, because ty is the definition, it's what we're defining. I can't write ty because I'd say what is ty.
So in the end, you can only fit in x with terms of your ty.
Well, x is going to become. So an object of this category is one of these things or one of those things.
Yeah.
And when you construct your initial algebra, it will be an object of this category, so it will have one of these things, and it will be, and you will call it ty.
But it doesn't mix with interpretation tn.
No. This is separate.
Yeah.
This is basically the definition of a functor on this category.
So this is. Anyway, please continue.
All right. So I will stop soon. You'll be pleased to know. I want to just talk about the serializability thing.
Yeah.
So
I mean,
this is
like the encoder and the decoder is identity.
Well, I will do something. So we chose this grammar. I chose this grammar, this universe, because Yellow was interested in it, and he was interested because it had this finiteness property which would allow you to serialize things. So in what I've done so far, I've not talked about the serialization. Now, of course, what you could do is separately, later, define a function. So, let's see. So we can now define a function like this, which would take, for any type, and any term of that type, I'll give you a string. Okay? And, you know, this is a map out of something which is an initial algebra into something else. So if you do it right, you would do this whole thing, and you could do it that way. And then what you're doing is you've got your grammar, and post hoc, you're serializing it. But I wonder whether there's a more sophisticated thing where you can build in serializability into your objects. Because this category just didn't mention serializability, we're just doing it afterwards. Let's see what would happen if we tried to do that.
So what is serializability exactly?
I can turn it into a string.
In a way that you can turn it back into.
I haven't done that. I didn't think about that.
So you want to have that like for all terms, doing encoding and decoding is the same as doing.
So I hadn't thought about that. So that's something more to do. We'll see if it can be done. You will at a later date. So let's go back.
Half an hour later.
I want to go back to just this original version of TM.
Yeah.
So remember here, the idea was we're going to build a set, call it ty, and a function from x to set, call it tm. But now, if we want to put this serializable encode in, I think we want to do something like, we want a set too big a writing. So a set, this will be our types, our codes, our names for types. And then for every code, I want to give you the set of terms that inhabit it, and a map from those terms into string. So just to compare it to here, if you drop this part off, you're saying I'm going to have a set, and for every element of I, I'll have a set. So that's what we had before, so I've added this part in. And if you look at this, of course, this is just fam of fam string. So do initial algebra semantics in here, and you'll automatically be building into your data type definition not just a set of codes, not just the fact that each code has some terms, but that each term then gets represented as a string. And it should just follow in the simple kind of way of reading off a functor. I haven't thought about going backwards. It's partial, I don't know, that's parsing.
Yeah, you might be able to do something with partial combinators.
Something, yeah.
Should it be J?
The nice thing about that is that.
Should it be J instead of J5?
Yeah, I was worried about that. I guess this should just well, yeah, maybe it's that. Maybe that will do. Yeah. And then this is clearly fam string. Because that's fam string. So this is signal I of type set, I arrow, fam string. Fam string.
That's not a dependent type, that's just an existential type. Even Haskell should do that.
Well, if you've got IO set, that's a dependent type. Yeah, but Haskell is acquiring dependent types. Okay, so let me stop there and just summarise again. So, data type theory, it's got a long history and done categorically. At a simple level, you take your little definitions of your simple data types and you can represent them categorically using these F-algebras and initial F-algebras. But as time has passed, we wanted more and more sophisticated data types, like red-black trees, I've meant to mention, like the untyped lambda terms. They were in that type 2 inductive types. You know? So you get more and more complicated things. It's unclear what the functional programming is. It's unclear what the introduction rules, the elimination rules, the computation rules are. There are other stuff, you know, like kind of the inductive reasoning versions of induction are. But the category theory seems to actually, when you get your head around it, cope with it. It's the same simple concept of an initial algebra, which I wrote on this board, which I still have on this board. That's all you need for data type theory. Very simple abstract definition. All you end up doing is choosing slightly more sophisticated categories to instantiate it in. So it's a real hit for category theory. I think in the end you could not really do advanced data types without this stuff. You might disagree if you're a type theorist, but if you're a type theorist, you're a category theorist in disguise. I better stop there. Thank you very much.